All right, welcome back. The next talk and the first of the afternoon is by Ryan Miller on Thomistic quantity and Cantorian number.
All right, thanks everyone for joining us, especially those of you for whom it's very early or very late. I wanted to say thanks for the participants so far. I think the flow has come together kind of more nicely than I expected, with first an outline of kind of Aristotle's views, then a sense of what the kind of landscape of neo-Aristotelian views is, then Daniel giving us kind of where Thomas kind of lands in that landscape, and I wholeheartedly endorse Daniel's reading of Aquinas, and then trying to show, or as I come in, trying to show how that links up maybe to more modern conceptions and concerns. So the dilemma here, I don't put it in terms of Benacerraf, but as Daniel did, but I think that's quite up to the same thing. So basically, I would say there, as James said, kind of two leading views in mathematical ontology right now. The first and more popular one is mathematical Platonism, under which numbers and other mathematical objects like sets or algebras or groups or whatever are non-physical, non-mental, non-spatial, non-temporal, non-causal, which is to say real abstract particulars. So this isn't quite Plato's own view because they're not causal, but it's the kind of the Phrygian Platonist view. And on the other hand, we have mathematical nominalism, under which numbers have only mental existence, either as constructions or as fictions. And this, I think, has come to a little bit of a stalemate, even though sociologically it's clear that the Platonists are winning, where mathematical Platonism respects certain intuitions, like that mathematical objects are discovered, not created, right? So when, someone thinks, oh, I've found the square root of 2 is irrational, and therefore we've discovered the irrational numbers. People don't think, oh, I've created the irrational numbers by doing a proof that the square root of 2 is not rational or something like that. That seems like a strange view. So we normally think of them as being discovered, which makes sense of them being kind of experimental objects somewhere. We might also think that they're what's quantified over in mathematical sentences. They're just ordinary terms as much as the terms of any other science. And so they ought to refer, right? If when biologists talk about species, predator species and prey species, that means that there are some species out there that are behaving in a certain relationship. Well, when mathematicians talk about operations forming a group, that should mean that there are operations and there are groups, and that the one somehow constitutes the other. They should refer in an ordinary way, and that mathematical sentences have objective truth values. So we might think that when you do a proof, that the conclusion is that the end of the proof, the theorem, is true. And that makes sense if objects are really out there, we're really referring to them, then we're making some claims about them. And if we make those claims in the right way on the basis of the right data, then, well, the claims will be true. So those are all intuitions that seem to favor Platonism. On the other hand, mathematical nominalism also has some intuitions in its favor. One is that the ontology just seems simpler, right? So mathematical Platonism asks us not only to believe in real abstract particulars at all, which many ontologies might think we can just do without, but also in a stupendous number of them, right? As Oystein pointed out this morning about transfinite numbers and the extent of the number line, that we're not even just talking about an infinity of them, as in maybe the cardinal numbers or something like that, but higher order infinities, and and on and on. So and not even a sort of unbounded one, right? Because we can just keep taking power sets. So this gets us just this massively inflated ontology. Whereas if they're nominalist and we just kind of construct them as we go, then we don't need to be concerned about having all these things cluttering our ontology. So that just Occam's razor seems to move in favor of nominalism. And another condition is the one of epistemic access, right? If mathematical objects are supposed to be, acausal and belong to some kind of other Platonistic realm, you might say, well, it's all well and good to say that you want to talk about them as if you discovered them, but how could you possibly discover them? Unlike Darwin, you can't go to the Galapagos and, and find the sets you're looking for, right? So what on earth would get you epistemic access to these objects that just come from another realm and have no causal interaction with the realm that you're part of? Doesn't make any sense. Whereas again, on a nominalistic view, if they're constructed or they're fictional, well, then of course we have epistemic access to them. We have epistemic access to all the things that we construct, or at least insofar as the one who constructs them shares them with us, then we have, or we read the fictions, then we have access to them. So there's no mystery there as there would be for the Platonist. And so maybe people think that they're more attached to the intuitions on the left than on the right, and that's why they're more Platonist than nominalists. But it's really hard to kind of get rid of either of these sets of intuitions, it seems. They both have a real pull on us, and that creates a certain deadlock in the debate. So then, what about Aristotelian Thomism? And most of what I say here applies to Aristotelianism in general. It's just that later on in the paper, I'm going to narrow down on Aquinas's interpretation. Well, here there are some advantages. So the idea here, right, as James Franklin laid out, for those of you here, they're somehow abstracted from real objects. So that gets us an easy story about discovery, reference, objective truth values, right? We start with the real objects, and we take something kind of from them. So why can we discover them? Well, because we're discovering something in the objects of the world. Why can we refer to them? Well, we're referring to something that's in real objects, some principle of them. Why do they have objective truth values? Because real objects do or don't have certain principles. So we don't need to worry about any of that. Epistemic access occurs via abstraction. Now, there might be something a bit opaque to many people in the contemporary philosophy of mind world about Aristotle and Aquinas' view of abstraction, and I'm not going to try to defend it here, but I'll just say it has a long history of defense, and it wasn't invented kind of ad hoc to solve a problem about mathematical objects, right? This is a really broad theory of how cognition works. So there's at least some story that's been defended for a long time about how the epistemic access works, which the Platonist doesn't really have. And so really, this should be taken to solve the kind of unreasonable effectiveness of mathematics. Oh, that's Benacerraf's version, Wigner's version, or whatever of the story. Because, unlike the question of, a Platonist object, which we then say, well, how could it apply to the material world since it just has nothing to do with it? Or a nominalist object where you might say, well, how can things that we've cooked up govern the world? It would be awfully strange if, we discovered, midichlorians or, magic wands or something just because they've been part of our fiction. If we went and discovered them in the world, that would be like a bizarre earth-shaking event, right? And so it would seem the same for mathematical objects. If mathematical objects are just constructed or fictionalized by us, why should they ever be effective in our physics? But here, if there's some part or principle of real things that we abstract from them, well, then of course they're going to be part of our theory of real things, which is physics. So that makes sense. All right, what about the drawbacks? Why wouldn't this view have taken hold? Or why, as James said, did it fall into disrepute in the 18th century? Well, one part is what I said about the theory of abstraction, which was attacked quite a lot by modern philosophers. Again, I'm not going to defend that in this talk, but I do want to flag that is, a relevant issue. The second is the question of reference. You might think, well, it looks like when mathematical sentences are written that they're referring to sets and other stuff as objects. And on the Aristotelian theory, they're not really objects, right? They're somehow derived from principles in this kind of indirect way. But I suggest that Pettigrew's free variable semantics kind of solves this problem and shows you a way that you can read the sentence correctly, get the semantics you want without treating these stuff as proper objects. Again, not going to discuss that in this talk because I think Pettigrew has done it and I'm not a philosopher of language, so it's both not a new contribution and one I'm not an expert on, but again, to flag something that has been an issue historically that I think is now solved. So that leaves two more issues, which are the substance of this talk. One is, look, for Aristotelians and for Thomists, mathematics is associated with something to do with quantity, as was said in several talks earlier today. But quantity is not quantity is something we abstract from material things. That explains all this, bit about the effectiveness and the science and all that stuff I was just talking about. But surely there can be numbers in the Aristotelian sense, or in some part of the Aristotelian or Thomist world, that are not objective material things. So when Aquinas says that there are 3 persons in God, or something like that, then obviously that's not an abstraction from the material world, right? It's not quantity in Aquinas' sense. So we might think, well, it looks like we've got kind of 2 bits doing the same work somehow. You already needed numbers in some kind of Platonic realm to handle cases like the number of angels, or, the number of divine persons, or even just to assign, true and false as 0 and 1 when you code stuff up or whatever. You needed some kind of Platonic numbers. And then now you're telling me that you're also getting numbers from quantities, from some principle of things. And now it just looks like you've just built up 2 parallel systems with different problems, and you have twice the pain. And this is not really following Occam's razor at all, as you promised us. So that's the first question that I'm going to try to deal with today. The second question becomes, the question has come up in the first 2 talks today, the question about infinity, and how can Aristotle handle the kind of infinities we need for Cantor's kind of set theoretic model mathematics. So that's the twofold project of the talk. Why do we need quantity at all to do math? And secondly, is quantity enough to do math? All right, so starting with the first question there, why do we need quantity if we already need some notion of number to deal with things before we ever had material things from which quantities could be abstracted? So the background to this is that there's 2 kinds of numbers in Aquinas, 2 sets of numbers in Aquinas. So the first he calls transcendental number. I think this must be sort of implicit in Aristotle as well, because Aristotle believes that there are things that don't have matter, that there are pure separate substances, separate forms, and we can talk about them, so we could presumably number them in some way. But it's explicit in Aquinas, and he gives it this name, transcendental number. And transcendental number is not abstracted from matter. And so examples would be, as I said, the divine persons, but also things that might seem closer to home. Like Aristotle wants to say there are categories, right? We have substance, quality, quantity, relation, et cetera, right? We go through, he lays out these categories, but the categories are supposed to cover, everything, not just material objects. In fact, quantity, from which, we get this other sense of number, is one of the categories. So the categories must be somehow prior to the sense of quantity, if quantity is going to be one of them. So in what sense do we say that there are 10 categories? It clearly can't be quantity. It's got to be something else. We'll call it transcendental number. And last, as I mentioned, the angels. But this kind of transcendental number clearly does assume logical non-identity, right? The 3 persons of the Trinity are not identical to each other. The 10 categories are not identical to each other. And it also presumes succession, right? The persons of the Trinity come in an order, Father, Son, and Spirit. The 10 categories come in an order, familiar to anyone who's, read Aristotle. So there's some kind of succession relation here as well. And if there's non-identity and succession, then it looks like we can use whatever this idea of transcendental number is, whatever that's supposed to mean, we can use it to define the ordinal numbers. And as we all know, that's a big step getting off the ground for mathematics. So once we have the ordinal numbers, we can do kind of more work, come up with more stuff. So that's why we need something else. On the other hand, we have magnitude. And so magnitude is a sense of number that's supposed to be abstracted from quantity. So the second category of quantity is some principle that inheres in things, and then, or the third category, and then second category, and then so it's part of every material thing, and we abstract from that. We get magnitude. And magnitude is supposed to be infinitely divisible. Right, so we're supposed to, if we have a surface that's of a body, because a body is a material body, it has a surface, and that surface we should be able to divide up however many times we want by bisecting it to get subsurfaces, etc. So these are 2 different kinds of numbers. All right, so why then would I think that the transcendental number is not enough for mathematics? Why would we need quantity? Why can't we just get by with transcendental number and not worry about this stuff that's coming from the world, and therefore kind of be Platonists? As James Franklin was saying, there's a certain role for maybe a difference of degree between a real Aristotelian and certain kinds of Neoplatonism. Aquinas himself, for various reasons that has nothing to do with mathematics or little to do with mathematics, is sometimes classed as a Neoplatonist. He was influenced by some Neoplatonists as well as Aristotle. So you might think, well, if you've got this kind of Neoplatonic realm of number, the transcendental numbers, why don't we just go with that? And I would suggest that there's an important story here. So for mathematics, we need not just sets, but groups. We need operators, right? It's not enough to just have, oh, look, the set of natural numbers, or, you know, the set of real numbers. No, we need to be able to do something with them to convert some into others. So at minimum, right, we need, you know, something like addition and multiplication, right? So then we talk about closure of the sets under these operators, things like closure of the groups under these operators. So a group is the set, but also plus some operator. But then I would suggest we don't just need any group, any operator at all. Like we don't just have what we need for mathematics if we just had addition and multiplication. No, we need a division ring. We need something with no non-trivial zero divisors. And in mathematics, really, that tells us it's the division rings that really give us what we reasonably call numbers. So Hurwitz's theorem tells us that the groups that have no non-trivial zero divisors and therefore are, properly speaking, division rings are the reals, the complex numbers, the quaternions, and the octonions, and there are no more. So you might have thought that just, naively, that just as you can take reals and then complex numbers, right? You have a real part and a complex part, and then surely we can double that again, and then you have a quaternion with, a real part, a complex part, and 2 more parts, and then you can double that whole structure again and get an octonion with 8 parts. You might have thought you could just keep going, and of course, from a certain perspective, nothing's stopping you from keeping going. You can certainly define groups that have these, more and more parts to them, and operators working over numbers that have, that look more and more like big vectors, right? Something stopping you from doing that formally, but what Hurwitz's theorem tells you is that what you won't do when you do that, if you keep going past the octonions, or if you try to define like a 6th place one or something like that in between one of these, what you will only get trivial zero divisors. You won't have a division ring anymore. So for mathematicians, when we're talking about numbers, we're really talking about real, complex, quaternion, and octonions at most, and those all have non-trivial, or those all have no non-trivial zero divisors. If you go beyond that, you will get non-trivial zero divisors. You won't have a division ring anymore. Okay, and I want to suggest this might be this should have remind us a little bit of something that we might have seen in school at some point when talking about different modes of collection of data, levels of measurement. So if you do a survey, right, and you ask people how happy you are today on a scale of 0 to 7, if you've done any social science research, you know that you can't just straightforwardly then talk about, say, the range or the, whatever other statistical data of those outputs. Why? Because we need to keep track of the different levels of measurement. So the first level of measurement is nominal measurement. So that's when you ask someone something like, are you happy today? Yes or no? And then you code that in your Excel spreadsheet as 0 and 1 or something like that. So the actual input is not, in a way, a number at all. You're just using the numbers to kind of represent some input. It's a purely nominal relationship between the number and the input. And then there's no structure at all, right? You can't say, well, on average, people are 50% happy because half people said yes, they're happy, half people said no. And you say, oh, look, there's an average. People are 50% happy. That's obviously meaningless, right? Because you can't average. There's no average of yes and no. You can say half people are happy, half people are unhappy, but you can't say that the average person is 50% happy because that's a meaningless concept. Then if we go up a level, we go to ordinal numbers. So these are numbers where at least you have some kind of order to them. So that's, again, like that how happy are you today is 0 to 7 scale, where we can now say, well, the person who put that they are a 7 today and a 6 tomorrow and a 5 the day after, we can say they're getting less happy over time. So there's at least some order to the numbers that are being put in. But we still can't really do averages because we don't know that there's the same amount of distance between each of those points, right? There's nothing kind of calibrating that scale to say that when you go from a 7 to a 6, that you've gotten less happy by the same amount as when you went from a 6 to a 5. You don't have that kind of calibration, so you can say that they're getting less happy, but you can't like put a slope on that graph and say how quickly they're getting less happy or anything like that. Then at a higher level measurement, we have interval measures. And you can think of a great example is something like a normal household thermometer, where it goes up, and the difference between a measurement of 18 degrees and 20 degrees is the same as the difference between 20 degrees and 22 degrees, right? So if the household thermometer falls 2 degrees each day, you're absolutely licensed to put a slope on that, right? And talk about a certain rate of decrease of the temperature. No problem. So we've got a little more structure than we did in the ordinal numbers. But if your household thermometer is calibrated in Celsius or Fahrenheit, as most of them are, you'll find that you still cannot divide with this, right? If you try to say it's 30% hotter today than yesterday, by which you mean the temperature went from 20 to 30, this will be incorrect, right? You've said something false. Because the zero is a purely stipulative zero on these scales. Well, it's not stipulative, it might be grounded in some natural fact, but it's not a real zero. It doesn't, nothing kind of grounds out there. So we don't have a proper ratio between two numbers, even though they share this kind of stipulative zero. So to do that, right, we know that you have to go to real units, to real scientific units, right? And so when you go to real scientific units of temperature, charge, or anything else, then you get a proper zero. And now you can talk about ratios. You can say this is twice as charged as that. This is twice the temperature of that in kelvins, right? Now you can really talk about these ratios. But notice that what we needed to do, so in order to get this kind of ratio data, what we needed was a number that might look just like the other numbers, right? In each case, you might have just the number 10 there as a nominal, ordinal, interval, or ratio bit of data, but somehow there's more structure embedded in it. And in the ratio case, what we know we can do is divide. That's what allows us to do ratios, doing division, right? So here we have a division ring, something that allows division. And that, according to Aquinas, is precisely what quantity is. Quantity is that kind of number which you can meaningfully divide. So the difference here between the kind of transcendental numbers that we had and quantity is that in transcendental number, you can say something like there are three members of the Trinity, right? So you have ordinal data here. You have not just nominal, we can't only number them, 1, the Father, 2, the Son, 3, the Spirit, but you can say, well, actually, we can count 1, 2, second, and a third, and they go in a certain order. So we have an ordinal there. But we don't have a ratio. I mean, famously so, right? So each is supposed to be fully God. You can't divide the Trinity by 3 and end up with 1/3 of God, right? So you don't have a division ring. You can't, division is not the supported operator there. And the same thing is true for our other examples, right? So if you have Aristotle's 10 categories and you cut them in half, you don't now have half of reality because we just have from substance through relations, and now we have half of reality. We've cut out the place, time, habit, the other half of reality. That's a meaningless statement. So you have 10 categories, yes, they're in a certain order, yes, but they're not in a ratio. You can't say how much of reality is contained under each category. That's not a meaningful thing to say. So these transcendental numbers don't give you the structure of ratio data. They don't give you a division ring. So I want to say in the modern sense that we use them in science, they don't really give you numbers, because this is precisely the property of numbers that singled out the reals, the complex, the quaternions, and octonions as numbers, which is just what mathematicians do. In order to do this, in order to get those things, you need division, you need a division ring. That's quantity, because it's quantity that's divisible. If you have a surface abstracted from a body, and you take it and split it down the middle, you really do have half the surface. That's a meaningful operation in a way it's not on transcendental number. So far from having kind of two parallel structures, one of transcendental number and one of quantity, which are supposed to somehow doing the same work, are duplicative, quantity does important work necessary for talking about number in a modern sense. The transcendental number simply doesn't do. All right. So if quantity is in that sense necessary for modern number, or at least necessary within the kind of Aristotelian schema, that transcendental number wasn't enough. Is it enough? Don't we also need some kind of Platonic or constructed stuff, especially because of infinities? This is of course, the big reason that, in addition to the kind of epistemic points about whether abstraction made sense, that really killed the Aristotelian view of mathematics. So looking at Cantor tells us that there are, importantly, two kinds of infinity, and we don't mean two kinds of infinities in the sense of numbers, like the number of the natural numbers versus the number of the reals, something like that, but rather there's two kind of ways of saying the word infinity. One is a potential infinity, and hopefully all of us from math class, often use this kind of shorthand of 0, 1, 2, 3, ... Just keep going. We all know what's coming next, right? We can fill this in, and we contrast that, according to Cantor, with actual infinities, which are given by these kind of comprehension axioms. So here there's some A such that the null cell is an element of A, and there's also an A that for all A is an element of A if A is the successor of what we already had in A. So here we have a succession relation we're using to build this set, but everything is kind of stated in one piece, right? We have one axiom. We don't have any ... It's not like Pareto arithmetic where you just have infinite axioms, right? We're not doing that. There's one axiom that gives us the comprehension of the infinite set that we want to talk about. And Cantor argues this is what we need for mathematics, and particularly in terms of what Anne Newsom was talking about this morning, in terms of grounding truth claims. The idea was that the potential infinities don't really ground the claims because you don't really have the thing you need to ground the claim. That truth claims should be grounded by real actual facts, right? If it's true in the actual world, it can't be grounded by the fact that it's merely possible, because the fact that it's merely possible wouldn't tell you about whether it's actual or not. So if we want our mathematical statements to be actually true, then or even necessarily true, then we're going to need something more than possibility. We need something we can look at and comprehend at once and say, yes, given this axiom, which I can state as such, we know that this theorem follows. But I want to suggest that both of these are actually found in Aquinas, contrary to what you might have heard, that Aquinas, the Aristotelian tradition, only give us potential infinities. Why? Well, potential infinity, any number is always given to succession by 1, and thus numbers by augmentation into infinity, right? So that's what we have here. We have 0, 1, 2, 3, and we just keep augmenting. We just keep splitting, right? So this is what Anne was saying about the dividing operation of the line. We have the line, we just keep slicing it. We can just keep slicing as long as we want, but there's no end to it. And here he wants to say that there's no such thing as an infinite number, because while you can keep going as far as you want, you don't ever hit an infinite number. That's the part of the point of Oyste's talk, right? So nothing numerable is infinite, he says, because the numeral must be passed through by number. Therefore, no number is infinite. You don't hit an infinite number. You just keep going, and you just keep, every natural number you get, there's no infinite natural number. You just keep getting a bigger and bigger one as you go through. And that, I agree with Cantor, is not enough for modern mathematics. However, Aquinas gives us another road. He says it's impossible to know discrete infinities for the reason that it is not possible to understand many things through one species. So this is that idea. You can't understand infinity as one thing after another because your mind can't do one thing after another. Your mind only gets so many steps. You can say, 1, 2, 3, you can stop there. You can do one more step, you can go to 4, but your mind, being a finite mind that can only make finite operations, will never get to the end of the series, right? So it's impossible to know discrete infinities. But if many things must be considered, he says, it's necessary that one be known after another. So if many things must be considered, it's necessary that one be known after another. But look at Cantor's definition of actual infinities here, or how he sets up actual infinities. Do we have to know one thing after another? I say no. What we know is the set all at once by its OR element, the empty set, and the successor relation. We know the set as a whole. We don't actually traverse through it. We don't know one thing after another. We look at that statement, we comprehend that statement, and we know is the set as a whole. And so, because we know the set as a whole, we know it in the same way that Aristotle says we know the line segments, right? So we don't know it as infinite. We don't know as slicing it into infinite points, but we know it as a whole, as the one line segment. So I'm saying it's the same thing here with these sets. We don't know them by traversing the members. We know them as one complete set. So with a nod to Ant's talk about domains, so Cantor was worried here that then we wouldn't have a truth maker, because if you take a kind of a Finian view of sets and truth makers, you might think that the set is grounded in its elements, and so if we don't have all the elements, then we wouldn't have any truth makers for truths about the set, because truths about the set are grounded in truths about the elements. But for Aristotle, this is wrong, right? For Aristotle, truth doesn't go from the matter, or ground doesn't flow from the matter up. We don't have the matter as foundational and grounding everything else. Rather, Aristotle says in metaphysics, form is actually what grounds the matter. And here, precisely what we have is the form. We have the form of the whole set, and that's what grounds the matter. That's what picks out what goes into the set. So because we think the form is fundamental, the form is grounding the truths about the set, we don't have Cantor's domain problem. So, so this, is exactly what Aquinas wants to support, I suggest. So look at the text from Aquinas, just the reminder from Cantor's on the left. It says, if some infinite were known through the way in which it is infinite, meaning one thing after another, the unboundedness, as Oisim was talking about, in no way could be perfectly known. If, however, it should be known not through the way in which it is infinite, then you'll be able to know it perfectly, because the ratio infinity befits quantity, according to Aristotle. And every quantity has from its own ratio and order of parts. It follows now that when it's apprehended part after part, the infinite will be known through the way in which it is infinite. So here we know not by part after part, but by the ratio of the set as a whole, which is just what I suggest Cantor gives us on the left, the ratio of the set as a whole. So we know it as a whole, as the ratio of the set, just as Aristotle says we know it as the whole line segment at once, and not by its parts. And in fact, in the commentary on Dionoma, you'll see him actually use mathematical induction and support the idea of mathematical induction. So if Cantor's argument rests on this idea that mathematical induction is a valid procedure to generate truths, well, Aquinas is happy with that and in fact uses it himself. So the conclusion: first, quantity is necessary to develop the notion of number we need for mathematics and physics. Transcendental number isn't enough. We need ratio, we need division rings. Second, quantity is sufficient as a basis for Cantorian actual infinities, because they're not quite actual infinities in Aquinas' sense. They're talking past each other. An actual infinity for Cantor just means no ... But for Aquinas, this means this exactly. You're comprehending it under one ratio, not under its infinity of ... So I would argue that Aristotelian Thomism uniquely avoids, unlike Platonism and nominalism, any sense of unreasonable effectiveness in mathematics. You've just extracted a principle from nature and used it in your description of nature, which is just what we would expect to do in physics.
All right. So I understand that the procedure has been, for the Q, is to virtually raise your hand rather than say anything in the chat, and this would put you in order. So yes, I see that there is one hand by Eduardo Berno.
Thank you. Thank you very much, Brian, for your talk. Very, very interesting. The many things I hadn't thought about. I have a question, though. If I understood correctly, in one of your slides, you mentioned the division of number into two kinds. One would be transcendental number and the other magnitude. I haven't found this distinction as such in St. Thomas. He divides, following Aristotle, quantity into multitude and magnitude. And if a multitude is numberable, then it is a number, or countable. We could say it is a number, and if the magnitude is measurable, then it is depending on the number of dimensions. It's a line, a surface, or a body or solid. So I was this led me a little bit wondering. Well, and by the way, St. Thomas makes another distinction between virtual quantity and dimensive quantity. Dimensive quantity is found only in bodies, so it would not be found, for instance, in the Trinity. And this dimensive quantity contains number in potency because it can be divided into discrete parts. So this led me wondering a bit about something I've worked on, which is St. Thomas says, and this follows Aristotle as well, that we define things, or each thing is defined from its principles. That sometimes we call the same thing, we call diverse things using the same name, but it does not have the same principles, so it's not really the same thing. I was wondering if we were really talking about the same thing when we're talking about mathematics. In fact, St. Thomas says that there is no mathematical science of quantity insofar as it is quantity, that treats of those things that belong to quantity insofar as it is quantity, because that belongs to metaphysics. So I was wondering how you take this distinction or this evolution out of the ancient mathematics, if you consider it a homogeneous development, or has there been an important change, and what it might be, this important change? That's it. Thank you.
Yeah, thanks. So he does mention, so I agree with what you're saying about the division on the side of magnitude and the other elements of quantity in there. I mean, I just wasn't going into that in this talk. But he does mention transcendental number once, or at least once. It's in let me. Commentary on the Metaphysics, Book 10, Lecture 4, number 1997. Yeah, so that's where it's found. And there's also a secondary source on that, Harris, Transcendental Multitude in Thomas Aquinas, which develops that a little bit more. I think he might find one or two more references. So that's kind of what it's based upon. I don't know that he always uses that term when he's kind of meaning that kind of thing. That's as you say, another question. But at least that's where it does. It really is a term from from Aquinas. Whether you could use virtual quantity or perhaps in other contexts, that's an interesting question. That I haven't really thought about. I have to go through and look at all the texts where he uses virtual quantity, right, to see, what the parameters on that are, and I haven't done that textual study, so couldn't tell you. But yeah, so the point was just to say, at least, that just here to try to meet the objection that, well, but don't you already have number? And I say, well, in some sense, yes, but not the number enough to do what you want to do in math, in modern math. All right, now in terms of the equivocation on mathematics. Yeah, I think that's probably true. I mean, Jacob Klein is kind of my source for these things, though I recognize he's a little bit heterodox sometimes. I do think there's a huge shift in what mathematics means, whether mathematics is even kind of one discipline, et cetera. Of course, the rise of algebraic geometry does a kind of unification that was unimaginable to the ancients and medievals. But my question is less about what Aquinas would say about mathematics or how he would use those words, interesting as a study as that might be in its own right, and more just the question, as James Franklin would put it, like, okay, for us as moderns, having mathematics as we do is the kind of neo-Aristotelian route of abstracting from matter the right route to go to build math, to build our sense of math. And here, so I'm trying to really argue for that conclusion here, rather than anything about what Aquinas would say about our concept of math.
Thank you. And to the point, yes, My interest is above all in principles. That's my main focus. So modern mathematics has many problems identifying the principles. Unfortunately, I see that Andrew Irvine left us. He would have great things to say about that. Thank you very much.
Okay, next in line is Bob Brent.
Yeah. Hi, Brian. Thanks for that. And I find your response about actual infinities pretty persuasive, so I appreciated that. This is kind of maybe out of left field, but I'm wondering if there's any relation that you know of between this distinction between terms of first intention and second intention, and then quantity and transcendental number. Just because I've been looking into things that had to do with the Trinity on that too. And that's one way that some people kind of respond to this, there's no, you can't have more than one God because there's not any matter there to divide, but yet you have three persons that aren't divided. So one response to that has to do with first intention versus second intention. And I wondered if there was any way that maps onto quantity versus transcendental number, or if that's just crazy. So,
well, I don't know that it's crazy. I'm a little worried about getting it over my head just because I haven't thought about how that relates to Trinity questions. And as you know, Trinity questions are deeply vexed and require the utmost precision. So that's not to say that the question's a bad one, but just to say I'm a little wary of speaking out of turn. I don't think that would be the distinction here. I mean, so off the top of my head, first intention, right, is the way in which the thing itself is intentional. So if I'm looking at something, I have an intentional relationship to that thing, that's first intention. And then if I actually want to talk about the species in my own mind, now that's second intention, right? So it seems to me that mathematics would have to be mostly dealing with second intentions, especially when we're dealing with infinities and stuff like that, because we're not trying to abstract from actually infinite sets. So this it actually tips very nicely into, I think, Lorenzo's research program and what we might talk about next, about how to kind of ground out this stuff in reality and the different ways of doing it. But let's just say that from my simplistic perspective on that, there's certain things that could be kind of first intentions in reality. Like if I have an N3 molecule, 3 nitrogens, I might say, look, there's a first intention there of 3 because I'm directly, I'm looking at, I have the form of nitrogen and I'm holding nitrogen, but not only one nitrogen, right? 3 of them, they're bonded. And so I might say right there's a first intention of 3. So maybe you could get a bit of math that way, but it seems like the vast majority of math is going to be talking about second intentions. But I don't see that as mapping very directly onto the kind of Trinity, or the transcendental number versus quantity distinction, because in transcendental numbers, presumably, we want to say that 3 is, really predicated to the Trinity, and that's not only something that's predicated kind of secondarily. At the same time,
think about something like 3 sets, right? So they don't have matter. So that's presumably not like quantity,
right? It's definitely not quantity.
Transcendental number, right?
Yeah,
but set theoretic object. I mean, all kinds of abstract objects would presumably be second intention sort of objects, right?
Right. That's right.
That's what I was thinking about, whether those two would map on it, but maybe they don't.
I don't think that really maps on, because I think the idea here is it's more about the structure inherent in the number, and whether that structure inherent in the number is something that just lets you add or whether it actually lets you divide. We probably have enough time for one more, given that we have the break in between.
1 minute, I guess.
Thank you, Ryan. And in regard to this remark about second intentions, my question about infinity is precisely if infinity could not be something like a second intention, in as much as second intentions are things predicated of first intention. And I wonder if infinity, in your view, would be a kind of a second nature given in the way we understand numbers or quantity when we say, for example, counting that in counting we could count to infinite. I don't know if I'm clear, but my question is if infinity could be seen such in this way.
Yeah, I think there's no question that there's second intentions, right? It's not abstracted from presently looking at an infinity of things or something like that. I just don't think that resolves the relevant problem, because to say that it's second intention still says, well, how does that work? I mean, I can't have an infinity of species in my mind either, right? I'm just a finite being. So then you still need to talk about something like comprehension as a whole versus comprehension by iteration, that kind of thing. So.
Okay, thank you.
All right, let's applaud Ryan again.
All right, so thank you. And conveniently, Lorenzo is up next. So you want to go ahead and, oh, yeah. Oh, good, we are recording. Okay, great. So yeah, go ahead, Lorenzo.